Okay, so welcome back. We're just going to have a look at activity 2. So what we're looking at now is hemoglobin with normal range. So here we have some data that relates to 30 individuals, 30 males that were tested for hemoglobin, 30 females that were tested for hemoglobin. We're going to just basically generate a normal range based on that data set. So the first thing, I've got an answer worksheet here. So just to remind me what I need to do, so I'm just going to quickly copy over the instructions, if you like, for the data set. So let's see, that I'm interested in. So the first thing to do is descriptive statistic analysis. So we use descriptive statistics. We select our data set. Note I've selected the top line because there's a label there which we can use as labels in first row, and I'm going to select the input range, which is here, and then I'm going to make sure that summary statistics is selected as well as confidence intervals. And so here we have our descriptive statistics that gives us some information about our data set. The next thing that we're going to look at is developing a frequency table and graph, obviously. I'm just going to paste that in. So we do exactly the same as we did before, where we generate a histogram plot. But before we can do that, we need to develop a bin range. So you might have remember from last week or last time that we looked at bin ranges. We looked at developing a frequency distribution. So what we have is we have some different data here, but what we understand is that we actually have a minimum value for females of 11.9 and a maximum value for males of 17.1. So our range for our bin range has to go from less than 11.9 or from 11.9 to 17.1. So, and that's really important for us because then we can actually capture all the data set. So I'm going to make a suggestion that we actually go from 11.5 all the way to 17.5 in terms of our bin range. So what we can do in terms of our bin range is we don't have to do the actual range. We can just put in our straight away our bin range. So we're going to go from count anything that's less than 11.5. Then we're going to go to 12.0 and then 12.5. Now if we select all of that data and we use the little square, we can drag it down until we get to about 17.5. So we need to do two more and one more. So we now have our bin range calculated. So I can now use the histogram plot, and the data that I want to select is the male data, and I want to ensure that I select my bin range. I'm not going to include labels because I haven't selected the label of the bin range, and I'm going to place it next to my data set, so next to my bin range. And I want a chart output, so I'm going to click OK. So here's the chart for males. So you could just put male frequency distribution. I'm just going to move this chart over a little bit so that we can put our female data set next to it. So then the next thing is obviously to select the histogram again, but select in this instance for our input range, female data. Our bin range is the same, and we just want to make sure that we select a different place to put it. So I'm going to put it next to the male information. We've got a chart output selected, so click OK. So we now have our distribution for our female population and our male population in terms of frequency distribution. So I'm just going to call this female, and obviously we don't really need to look at the bin range again, so we're perfectly justified in actually moving the female frequency across and replacing the data. Okay. Okay, so the next thing to do then is we're going to look at developing a normal distribution for our data set. So I'm going to create a new sheet. I'm just going to highlight where we're at on the terms of the answer sheet. So we're going to look at male and female. We're going to develop a normal range, and then we're going to actually draw a normal distribution for the whole population based on this sample. And that can be quite interesting to look at how different the distributions and variances within distributions may be, but also how the means are shifting across the two cohorts. So in this instance, we have a female distribution and a male distribution, and when we overlay them into graphical representations, you can see how different the hemoglobin distributions are. So the male distribution is a little bit wider, a little bit more varied, I suppose, from the female distribution based on this data set. So the first thing we're going to do is we're going to have to calculate our manual SDs. We could use the descriptive statistics for the mean and SD, but I'm just going to copy this over to our worksheet here, just to sort of kind of give you an indication of what we're doing. So the mean is obviously using the equation average. Median, again, median. Mode is using the mode function. SD is using the standard deviation function. And indeed, SEM is basically the standard deviation divided by the square root of the count of data points, i.e. square root of n, essentially. And that's how we generate our standard error of the mean. And these should all relate back nicely to the standard deviation, standard error of the mean for all of our data and our descriptive statistics. So you could quite easily refer to this data if you wanted to, as opposed to doing the analysis again. So the first thing to do then is obviously determine the normal range. So in determining the normal range, a normal range usually, not always, but usually is defined as being plus or minus 2 standard deviations. Now what that really means in effect is that you're going to capture 95% of the population. So you end up capturing 95% of the population within your 2 standard errors of the mean. So if we take our mean value, so this is going to then be male, it's going to then be female, we can essentially extract that mean from here. And what we want to do is paste special, and we want to paste special the values rather than actually the equation, right? So hope you saw that. What you have is a number of different associated paste specials. So it's paste special values basically just takes the number and copies and pastes it into the area that you want it to be pasted. And then we have our standard deviation. So what in terms of our lower normal range, lower value if you like, what we have is we would have our mean minus 2 times our standard deviation. Okay, so in essence you could use this equation, and that should work, and then we can also obviously track it across and get our lower values. So I just want to quickly double check that that's correct. 11.61 and 13. Yeah, so if we actually reduce the number of zeros because it's ridiculous, we can just go up to 13.00 and indeed 11.61 and 13.3, 15.8. Okay, and our upper values are basically the same thing. Okay, so but we obviously, rather than minusing, we actually add in this instance. So I'm just going to copy that and escape, and then I'm going to paste it in. Oops. Paste it in here. Now we're referring to our mean and our standard deviation, but this instance we want to actually add. So we're just going to add the value, because we've got silly decimal places, we only really want 2 standard deviations, 2 decimal places. Then we now have our upper value. So the normal range for male hemoglobin is from 13 to 17.36 and 11.61 to 15 for females. So we now have a normal range or reference range for our laboratory. Now the next thing is a little bit more complex in terms of defining the normal distribution based upon this sample. So normal distribution is defined by your standard deviation and your mean. And so one of the things that we can do is we can develop a distribution table. Sorry, that's the wrong one. Based upon the SD increments that you want to plot, male, and you can normalize using a n-dist or normal distribution equation. So I'm just going to quickly copy this over so that we have an example that I can take you through. So what we have is we have our SD increment of -3. We have our reference, remembering the dollar signs mean that you're fixing the point. And basically what we've done is we've taken the mean, we've taken away the 3 standard deviations, which equals 11.91. We can normalize this using a normal distribution. So F10 relates to the value here of F10. So this is the X value. Then we have the mean in terms of our mean, and then we have our standard deviation, and it's basically asking, do we want it to be cumulative, i.e. adding on top of one another? And obviously we don't, because we want to generate a nice Gaussian distribution. So we now have our first normalized data set. For females, it's essentially the same. We're just referring to a different data set. So we're referring to mean and standard deviation here. So in terms of the scale and how we might want to utilize these increments, what we have is we want to run from plus or minus 3 standard deviations. So here, so we've got -3, -2, -1, 0, +1, +2, +3, and obviously 0.1 in divisions in between. So when we're looking at our data set, we need to basically ensure that we're referring to this this multiplication. So this will be multiplied by 2.9 as opposed to by 3. Oops, wrong. So by dragging it down, it's not going to work. So what we need to do is put it in as 2.9. And I'm just going to make sure we're not filling to make it look a bit neater. So we now have, when it's -2.9 standard deviations, the X value will be 12.01. So this, if we drag this down, it should change the reference point to F11. So I'm just going to give it a go and just make sure it does. And it does. Okay. So the idea being that what we're going to look at now is essentially dragging down the information so that we can actually refer to it more effectively. So I'm just going to remove the coloration that I've got in the graph. So in order to streamline this, what you can do is you can use a slightly different equation. So what we're doing is essentially taking our previous value for the males. We're still referring to the standard deviation, but we're dividing by 10. So what we're doing is we're essentially taking this mean value, we're adding us the standard deviation, but dividing by 10. So we're reducing the standard deviation by 0.1 each time, which is essentially what we're doing here. And so each time we are referring back to the previous data set. So I'm just going to quickly run that through on here. So what we actually have here is not times 2.9, but we have it divided by 10, and we're adding on top of this value here, okay? And you've got 12.1. And so what will happen is, because we've got reference to our standard deviation, if we drag our data down, we should then be able to see it changing in accordance with the normal distribution. So these are now our plus or minus 3 standard deviations in terms of our haemoglobin value. The next thing that we need to do is we need to look at this value and its normal distribution. Okay, so and again, because we're referring to a movable object in terms of the F column, in terms of this data set reference point, we can just drag it down and it will generate our normal distribution curve. So when we're looking at developing an actual chart of this data set, what we can do is we can use a line graph, and we can refer to specific data. So if we choose a line graph, in this instance, what we have is we've selected not quite all the data, so let's just select all the data and choose a line graph. So this then is our line graph, but obviously the data set that's on the x-axis isn't related to our standard deviation, so we need to change that in terms of our data set. And similarly, you would do exactly the same for the females. So then you can build a graph very much like this normal distribution graph here, where we now have our hemoglobin value, and we can identify the points at which a standard deviation of plus or minus 2 occurs, and indeed identify the normal range, the mean, and even you can identify the points at which you have plus or minus 1 standard deviation, plus or minus 2 standard deviations, and indeed obviously plus or minus 3 standard deviations. So I hope that's been helpful in terms of developing a normal distribution curve.